Okay, I want to thank you all for joining today. This is our 2023 OCP Storage Tech Talk. Sorry, we're starting a couple minutes late. I also want to thank our sponsors. We have Purdue, Silicon Motion, and Micron. I want to thank you all for sponsoring today's event, as that helps us out a lot. And with that, I'm Ross. We also have Amber here, and we will be your facilitators today, and we look forward to a great session. Let's start off with, let's head on celebrating some of our wins here. So in 2022, we had the NVMe HDD Rev 0.7, Barton Springs, Grand Canyon, the Poseidon E1S storage box, and the Hyperscale NVMe boot spec. Now to 2023, we have the NVMe HDD Rev 1.0, an Enterprise Edge Gateway, the Datacenter SATA device spec, and coming soon, we have the Datacenter NVMe SSD Rev 2.5. So as you can see, we have a broad portfolio of specs that's moving the industry forward. Some agenda here. We'll make it to the welcome, and then we'll go to flexible data placement, and then we'll talk about Grand Canyon YV3 flash boxes, the regulatory environment for storage. We'll talk about enhancing fleet health monitoring. We'll have a little break if there's time. Then we have some device specification updates. Then we'll talk about customer problems and requirements and a few closing remarks. So with that, how about if we get rolling here? I should also add as a call to action, please be present for this great content and engage. And think about help defining the future for the storage project. Think about identifying areas for future collaboration. So with that, we'll start off with flexible data placement. And we'll start off here with the State of the Union. And Chris, you want to take it away here?
Sure, yeah. So I think just to start from the very beginning, what is write amplification? So when a host sends write data to an SSD or a device, it's the additional data that's written to media. So a useful term here is write amplification factor, which is just the amount of data written to the media divided by the total that the host intended to write to or data that the host intended to write. So for example, let's say we had a WAF of this example of WAF 2.5. So the host writes 1 megabyte of data. The device writes 2.5 megabytes of data to the media on the back end. And that's composed of the 1 megabyte of host data and an additional 1.5 megabytes of garbage collected data. So that results in this extra 1.5 megabytes of work that's done that the host really didn't necessarily require. Next slide. So why is this undesired? So these extra media reads and writes result in an impact to performance QoS, right? We get those extra write. The write throughput drops. There's the extra writes potentially impact reads, tail latencies, all sorts of negative effects. So there's also an impact on media wear out, right? Those extra writes are taken out of the total lifetime of the flash memory cells. In addition, there's extra power, right? Writes are power intensive, and so running with a higher write amplification results in more power consumption, more TCO. So for example here, in an ideal world where we have a write amplification factor of 1, a random write performance looks the same as our sequential write performance. Whereas if we've got a write amplification of 5, then our random writes are going to look at best like 20% of our sequential write performance. Next slide.
Right.
Sorry.
It's not. There we go. I don't know why it wasn't going forward. Okay.
So here's a little timeline of kind of state of the art in write amplification. So kind of in the beginning, NAND-based SSDs in the early 90s. The one lever that we had, the tool that existed, was over provisioning, right? So if I keep 20% of the media spare instead of 10%, now I've reduced write amplification because the drive has more wiggle room to play with. You know, circa, you know, the mid 2000s, 2007 or 8, trim sort of caught on, and this is the ability for the host to indicate when data is no longer needed, which sort of allows the drive to, you know, to be more efficient on garbage collection decisions. So then, you know, skip forward to now, and we're talking about FTP, and this kind of is the next logical leap in improving WAF and getting some of the benefits, reducing the impacts of write amplification. Next slide. So how did this come about? So at Google, we were working on a write amplification improvement strategy. You know, the key we decided was that the data placement on the media, and we came up with the smart FTL proposal. In parallel, and I think we talked about it at OCP here, you know, in the fall, like 2 years ago, or a year and a half, yeah, 2 years, almost 2 years ago. And then in parallel, you know, Meta was also doing their write amplification investigation, and they decided that the placement on the media was key, and they were working at the same time in parallel on this direct placement mode proposal. So we work together, and we sort of, you know, try and take the best of both, and that is what became flexible data placement. And you know, today it's fully ratified. This is TP 4146. There's a link here in the slides. You can download it from the NVMe Express, NVM Express website. Next slide. So a high-level overview. So basically, what does FTP do? It basically gives a hint. The host allows the host to provide a write hint on where to place data via virtual handler pointer. So the changes in the device are really, it places data into a specified superblock instead of one that it's chosen. The device advertises the size of this block. So what doesn't change? So reads are totally unimpacted. Writes, there's an optional tag that you can put. You don't have to provide a specific tag. Deallocates and trims are unimpacted. Security is unimpacted. So one of the big benefits of this is just backwards compatibility. It could be enabled on stock standard devices as an incremental functionality. Applications aren't fundamentally required to understand FTP to get some benefits, but applications that do fully understand FTP have the ability to increase those benefits and really optimize for FTP functionality. Ross, did you want to take over here?
Sure, I can take over here. So let's talk about some of the open source activities going on here. So in the Linux kernel, there's full I/O pass-through since 5.19. XAVME also has full support. QAMU has also added support. FIO, it has basic support for RU and RUH, and they're working on some improved generic IO trim and IO U-ring that's still ongoing. NVMe CLI supports FTP commands and log pages, and CacheLib's work is ongoing. So as you can see here, you know, this is ratified in December, and the open source activities are ramping up. Some comments about the Linux kernel. And IO pass-through enables any NVMe device to be available in Linux. So it removes block layer limitations. It's implemented in IO U-ring, so it has scalability and performance. Supports end-to-end innovation for new interfaces through the in-kernel IO. Supports the stacks. This is since 5.19. If you go to the right of the slide, you'll see how the in-kernel substituted SPDK for the NVMe driver using a generic device. And it's a generic way to do async ioctals using IO U-ring. And a generic device is always available, and user-managed IO kernel managed device. So anyway, the IO pass-through is a very nice solution. So as a summary, we talked about specifications and all the open source activities that are ongoing and have completed. The ecosystem is ramping up quickly. So I'd encourage you to bring your applications, use cases, and discussions about this to the monthly OCP storage meeting. I think soon we're going to start seeing lots of people present lots of ideas, data, interesting things. So bring it to the meeting and we'd be glad to discuss it. And with that, we're going to go to supplier panel. For our supplier panel, we have Jamie Song from Fadoo, who I think he's our longest presenter here today. He's presenting from Korea. We have Matt Rosick from Kioxia, Luca Burt from Micron, Mike Allison from Samsung, David Wang from Silicon Motion, and Dave Landsman from Western Digital. So with that, let's go to Jamie here. So Jamie, here we go.
Yeah. Hi everyone, I'm Jamie Song from Purdue Technology, and it is great opportunity for me to have a talk in OCP Storage Tech Talk. I'd like to share some idea on FTP from a supplier's point of view regarding its key difference compared to other stream interfaces, and one suggestion for its broader industry adoption. There has been quite a long history of open channel style of industry specification effort, including multi-stream, GNS, finally FTP ratified into NVMe in 2022. I will not explain further for the common motivation of this spec because it is already covered many times. In general, there are two core goals to be pursued for all specification efforts, which is in trade-off relation. If you pursue design flexibility more, it's good for adapting more customer needs and incorporating various controller and vendor solutions into ecosystem. But on the other hand, the implementation inefficiency, for example, longer development time, larger controller size, could be caused by kind of over-engineering. Meanwhile, if you pursue more specific implementation guidance, it greatly helps making implementation easier and more efficient because there exists less ambiguity in spec. However, if you specify too much detail, it also could limit various customer needs and extensibility. In my opinion, compared to multi-stream spec, FTP achieved more balance point between these two somehow conflicting goals, so that SSD supplier could provide more solid product with better quality within shorter time frame, while providing the benefit of decreased WAP of SSD to the customer. Next page.
Give me a sec, the slide is not advancing. Okay, sorry about that.
Okay, it's fine. As a controller solution provider, I have one idea for promoting FTP spec for bringing more suppliers into its ecosystem. FTP spec provides a spectrum of different reclaim unit sizes and the number of reclaim groups depending on various customer use cases. If customer A adapts one big superblock, which consists of dies from all NAND channels, the host software has less control on data placement, but the data's reliability, which might be threatened by NAND die failure, could be overcome by SSD's internal RAID recovery more easily. On the other side, if customer B adapts smaller reclaim unit size, let's say a single physical block in a single NAND die, the host software will have much more flexibility and control, potentially better optimization for their own workload, but the data's reliability issue might need to rely on host software's data redundancy scheme because SSD controller might not support enough SRAM for actual RAID buffer. To address this problem, the customer controller vendors and NAND vendors should gather and discuss together to figure out what the solution is to meet requirements. As As a controller solution provider, I wonder what if there is some spec or guidance on additional requirement on reclaim units error characteristic so that we better understand customer needs and put relevant design into our next generation controller. We believe that this could provide a momentum to start a new design and engineering effort for the supplier who wants to take part in FTP ecosystems. Yeah, thank you for listening to my talk.
Thank you, Jamie. Next up, we have Matt Rosick from Kioxia.
Thank you, Ross. So there's been a lot of talk already about WAF and other things like that. Oh, did it go away? Okay. And you know, as it is, I think most people know that the SSD will store the host data in units called superblocks, as Jamie just talked about and Chris was talking about earlier. And in order to make sure that we're maintaining performance and good quality of service, there always needs to be some spare superblocks available to fill. When the current one fills up, it can just move the right pointer over. And to do this, you know, the garbage collection that's going on, finding superblocks out there that have some invalids in there, it's picking and it's combining those. And to keep consistent performance, you want to do that spare superblock creation or that garbage collection soon, but you don't want to do it too soon because you might be picking a superblock that might have some other deallocates coming to it fairly soon, and you could pick the wrong one, and the SSD itself could be increasing the write amp on there. So, and now we go to the case where in FTP, and instead of just needing, say, one spare superblock for the pointer for host writes, if you have 8 reclaim units or 16 reclaim units, the number of spare superblocks needed goes up a fair amount. So, you know, the question is how would that play into garbage collection? Is it going to really make it so you need a lot more write amp and bandwidth for that GC? And, you know, even there, if you need that, will that actually impact the amount of utilization that the host may have in order to maintain a certain user experience or host use of that drive? So if we go on and take a look at the next slide. And so what I have over here on the left is a conventional drive. And in this case, the host has been going through, it's been deallocating, but as these writes were coming in, they were getting intermixed. So if it did a deallocate on a particular range of LBAs, it might poke holes in here. So just real quick, the colors are gray as the superblock is completely full. There's no holes in it or no invalid data. And then you go something from a color that's in the red, which has a few holes poked in it, to something that's fully green, which is it has been fully deallocated and ready for the right pointer to ship to it, be erased and start getting writes. So between the two of them, you can see that not only on the conventional one, there's only 15 free blocks and the drive is 87% utilized. And you can go to an FTP case on the right, and here there's 82 free blocks available and the drive is 94% utilized. So in this case, you can see that a well-managed FTP device would actually help in terms of write amp. It has all of the necessary superblocks. It reduces your garbage collection. So all in all, it really will add a lot of benefit in terms of write amp. So more of the endurance is actually available to the host, or PE cycles are available to the host versus the system, and you'll get better performance throughout. And so that's what I have, Ross. I think we can go on.
Thank you, Matt.
Yep. Yeah.
Next up, we have Luca from Micron.
Okay, thank you, Ross. I want to bring this discussion a little bit of different direction. You have heard from previous presenter, and we'll hear from the following one all the goodies and the value of FTP, which is absolutely I completely endorse it. But one of the points that we are looking also is that FDP, by its own nature, like all these type of interface changes, in order to get the benefit, you need to have a software stack on the host, application, database, file system, whatever you use over there that is FDP aware, ported to FDP. And the reality is not everything can be ported to FDP. Sometimes you cannot because you do not have the right infrastructure. Maybe use file systems that are not amenable to the changes, or you have a customer base that is not willing to accept the changes like this level over here. So one question we are asking ourselves is that, is there any situation where these legacy applications that are completely unmodified, they are not aware of FDP, can they benefit of it in one way or the other? And the answer is, well, it depends. It depends on what you do. It depends on your configuration. But one of the areas that we are looking into is a system where the SSD is exposing namespaces that are attached to multiple different applications. If you look to the pictures on the right, starting from the top is the conventional SSD that happened today. In this case, I assume that there are 4 different namespaces connected to 4 different applications, which is not unusual. One thing I want to point out is that one of the subclass of this configuration is when you have virtual machine. When you have virtual machine, this is almost always the case. And by the way, when you have virtual machine, you probably do not have 4 of them like in this picture. You may have tens, even hundreds. So this is an oversimplification just to make the point that think about anything where you are exposing the same SSD and sharing and having multiple namespaces shared to different applications. The conventional design today on the top, all these applications, they write in different namespaces, but the data get mixed in the back end, and you get this type of colorful vertical pile that you see on the right that represent a superblock, where components from each namespace are written in the order they come or with some policy, but they tend to get sort of mixed together. This is one of the big problems that created the write amplification that Chris Abol mentioned earlier on. This is very difficult to manage and to keep things in order. Now, if you think about what happened with FDP, if you go to the bottom right picture, exactly the same type of configuration. One may think about that the concept of region is built in the SSD, and each namespace may be assigned to a different region. So the namespace 1, for example, the green color may have the green region, and the purple one, names 2 with the second region, and so on. So each data can be written in a different region, and we'll be able to keep the data separation, which is the biggest step forward to remove write amplification. And this can be done with the existing infrastructure, just using internally the proper assignment. But whatever is outside the SSD is just standard. Applications are not even aware that the SSD in the backend is using that. And this is, in theory, bringing some significant value. But how much is it? I mean, so much for theoretical discussion. Can we quantify it? So, Ross, can you go to the next slide?
Sure.
So we're trying to quantify it, and we start with something simple and to get something a little bit more complicated. So what we did is that at the beginning, let's try to use some synthetic workload using FIO basically as a workload generator, and then move on and connect to real benchmark and so on. What we do using FIO, we say, okay, let's use the 2 different corners. The first corner is let's assume that the same 4 applications that you have above are doing sequential writes. This is a write amplification, so only write matter. Read are completely independent. So let's focus on write. So different sequential write, but remember, each one is sequential write is a different application on different regions. So each application is sequential, but the data tend to be mixed together. Even if you have 2 sequential streams that get mixed together, you get this butterfly effect where components of one are mixed with the component with the other, and the different speed of each application just give different type of mixes. That's an optimistic case. Overly optimistic, maybe so, but is similar to what happened with file system that do write login and every type of application that use this log write. You will be surprised to see how many applications are based on sequential streams. But this creates, let's say, a ceiling of improvement. And if you look to the table that I have written over there, we run that application. We have details on configuration if needed, and the difference in write amplification is from 1.63 with the conventional SSDs go down to pretty much 1. Now, this is 37% improvement, but remember, 1 is the floor also. The write amplification cannot be below 1 by definition. You write so many data, you get so many data on NAND. So this is actually almost complete elimination of every write amplification. Very optimistic, maybe, but closer to reality than people may think. Then we try to run something that is more pessimistic. We go to JEDEC workload. We used both the 512 byte and the 4K mixer. 512 byte is problematic, but is not that common. This constitutes, if you want, a floor, meaning this is the most difficult case to handle, and actually is overly so because it has a lot of random data. File systems are never random. Data are never random. There is always ties between them, which will make this configuration much better. But even there, we get about 7% with 4K, which is improvement, only with 4. And remember, if you grow the number of namespaces in application, this number only tend to go up. And then there is the last one, which is running full benchmark, which we really hope to present data today. But believe me, running full benchmark is extremely more complicated than running the other two. So we'll update this table later on in different events. But the starting point is that even applications that are not aware of FDP, but are using multiple namespaces may be able to benefit of FDP significantly. And this is very important to make FDP distributed in the market to get enough inertia to make it happen, because it will be able to affect even non-FDP applications. Thank you all. Ross, back to you.
Thank you, Luca. Next up, we have Mike Allison from Samsung.
Hello, my name is Mike Allison.
Go ahead, Mike, I have your table up.
Okay, can you hear me?
Yep, we're good.
All right. So I'm the lead author of the FDP protocol, and it was really a consortium of a lot of different companies putting this all together. But I keep getting asked, what's the difference between the different placement capabilities within NVMe Express? So this table is to compare streams, flexible data placement, which I'll say FDP from now on, and zone namespaces. And I'm not going to go through every entry of this thing, but I have highlighted the 3 that I do care about. One of the advantages of these data placement is to minimize WAF, but it requires that the host has a protocol that adapts to the particular feature to minimize garbage collection, as we've been talking about. And one of the biggest differences between streams and FDP and zone namespaces is, how does the host know if it's not honoring the protocol? And one of the things about FDP is it's going to let you know in a log page to tell you, hey, you're not conforming host, but I went ahead and did your writes, and you can go fix your software to adapt where you want to adapt. Whereas in the other places, you either don't know, or you could get an error back if you're not aligning to the protocol. And then the other one is, all right, you have these things that we're calling reclaim units or stream gradual sizes or zones between them. And how do you know, how does the host software always know if he's aligned where he wants to be within those capacity containers provided by these capabilities? And in ZNS, you're always aligned. You have to adhere to the rules, and you always know where you are because you're writing at an exact point within a zone. Streams, after streams are enabled, you're always know where the start of the stream is when you first format the namespace, and then after that, there is no feedback. FDP has the ability for the host to query where they are and to actually move from one reclaim unit to the next. And then lastly, we've been all talking about WAF. And what I really want to point out is the ZNS gives you a WAF of 1 by definition. Whereas streams and flexible data placement, if the host does change all of their firmware to abide by the protocol, you can achieve a WAF of 1 by making sure that any user data written into the storage is actually deallocated or written to another container of that storage before garbage collection would have to happen. And it kind of goes in with this backwards compatibility that's on the line that I didn't highlight there. Because it's backwards compatible, the host gets to choose what data gets to be moved to apply to FTP and look at the cost of changing that host software to the savings in WAF. And if the cost is, if there's a benefit, then change the software. If there's not a benefit, then the host can say, well, I don't want to go change this. And maybe having a WAF approximately equal to 1 is good enough for me for my cost benefits. Next slide, please.
Okay. I'm not sure if you can see this, Mike. I know you're struggling. I got simple SSD versus conventional.
Yeah, just go ahead and click because it showed it. Go ahead and show all the text. I'll just talk through. I wasn't sure if you're going to show the thing.
I clicked through your text.
All right. So if you look at FTP, it has this thing called reclaim unit handles, which are basically write resources. And it has reclaim units, which in this case I'm showing you as super blocks, as everybody else has talked about super blocks. And if you only have one reclaim unit handle and one reclaim unit group for all those super blocks to exist in, then when you look at the reclaim unit handle, that can either be defined as an initially isolated or persistently isolated, it behaves the same from the controller point of view. There is no difference because there's a 1-to-1 ratio in the reclaim unit handles and how they adapt. And if you really look at this here, it really matches a conventional SSD. This is what happens. You write, every namespace shares the same resource. It all writes into the super block that's referenced by the reclaim unit handle, and you mix the data. So the point of this whole slide is for implementers, you can create an FTP only SSD, create a single FTP configuration that only has one reclaim unit handle, one reclaim unit group, and all of your reclaim units within there. And you basically have a conventional SSD. So you only really need to create an FTP enabled device. And when FTP is disabled, just by default, use this configuration. And that's all I have to say. Thank you.
Thank you, Mike. Let's go to David Wang at Silicon Motion here. Okay, David, we'll let you offer your thoughts on FTP implementation here. We can't hear you. You're muted. If you're a little closer to your mic, it might help. We can't quite hear you.
Can you hear me?
Now we can hear you.
Oh, this is nice. Okay. Yeah, we already know FTP can help reduce the write amplification, but from the controller vendor, we are seeing many challenges in the FTP implementation. So yeah, there's some fact we want to share and some thoughts about how to help the FTP implementation. The first fact is FTP application usually need a big number for open super blocks, such as 8, 16, 32 or more. The second factor is with a large RU size, we have more challenge in the because we will see lots of write collision, means the write point is in the same die. So this means we need more write buffer. Actually, Jerry also raised another point is for the small RU size. This means we need a more read parity buffer if we need to support the read protection for the small RU size. So yeah, all the fact is imply we need a much bigger write resource in the data path, including the write buffer and the read parity buffer. Here's our some idea is the first one, use a two-stage buffer, including the SRAM and DRAM for the data manipulation and programming, respectively. The second one is the flexible read encoding order to reduce the parity buffer use per open IU. Yeah, we can have some option. Working encoder is in the word line in the each die first, or is in encoder is flash page, and then the next die cross channel. Yeah, this is some option we can consider from the implementation. Go to the next page. Yeah, another fact is about if a multiple host application with a different place ID may have different write throughput or performance requirement, right? But the controller has no such intelligence, and usually it's equally or statically allocate write resource for each open IU. Actually, yeah, we can see there's a gap here. So ideally, in the controller side, we should allocate an appropriate portion of write resource for meet the performance need in each application. Yeah, but it seems, yeah, we definitely in the controller side, so far FTP has no such information. So we have some suggestion to may consider add some performance metric information in the IOH level, as it can help controller to allocate a resource or do the QoS control. Yeah, this is our idea in the implementation side. Thank you, Ross.
Okay, thank you, David. Next up, we have David Landsman at Western Digital.
Thanks, Ross. Can you all hear me okay?
Yep, you're great.
Okay, good. So I'm kind of going to stick with the theme that Mike Allison was talking about. And just a quick history here. From a standards perspective, oh wait, I should turn my, there. I think my video will be on now, right? There, sorry. So from a standards perspective, we've been on quite a journey, as people have talked about, to get to FTP. And I think, we had a common goal, which was largely around reducing write amp, which allows you to reduce what the drive has to do for garbage collection, which in turn gives you better endurance, better throughput, and more predictable performance. And from being a longtime NVMe board member and also as a device vendor, I really hope that we can start. We've been trying to define a problem in one way, and we just haven't quite gotten there in a long time. But I think that with the emergence of FTP, we're getting really close. So let's go to the second slide. So I think the way we've emerged out of this wandering journey, and I think I see two lanes kind of happening in the marketplace for SSD placement. And one is FTP, which is really focused on SSDs. And the other is the ZNS zone storage ecosystem, which is not only SSD, but trying to harmonize with the SMR HDD ecosystem. And that's one of the reasons that's one of its core goals. Now, I view FTP as kind of having emerged out of a need for, if we look at the use cases of these two, FTP kind of emerged out of a compute use case. It wasn't primarily focused on capacity or cost. It wanted to use the same standard block device with, using the, like if TLC was the main center point of NAND, it wasn't overly concerned about trying to use QLC or PLC or the highest bit, the most compact NAND. It wanted to use mainstream NAND, standard device, standard standard amounts of DRAM, and so the FTP is kind of this compute thing. And then on ZNS, although it could be used in many ways, just like any interface can be used in many ways, ZNS is kind of oriented towards this capacity cost point where we're willing to use a specialized device and invest in a specialized device, and we're looking to get QLC or above and the lowest cost point for the SSD device. And another contrast in use cases is that with FTP, as other speakers have mentioned, the host software changes are kind of optional, although I think that's going to be an evolving thing. To really get performance out of FTP, we'll have to invest in software optimization at the host throughout the stack. And the same really is true with the zone storage ecosystem. But we've always assumed that if you're going for a sequential write required model, which is really this zone storage model, you're going to need to invest in the software stack to serialize your I/O. So if we look quickly at the protocol contrasts, again, I see FTP is kind of a loose contract. You have it's more of a, it's not entirely accurate to say this, but it's more streams-like in its nature. It's delegating more of the placement efforts to the device, although the host is using hints to guide the device. It doesn't require host writes in any particular order, whereas ZNS is more of a tight contract between the host and the device, as is the case with SMR. And non-sequential writes are, in the current instantiation of ZNS, non-sequential writes are rejected. So that's the last slide. I think it's good to keep the two of these endpoints in perspective. And I hope that as a community, we can stabilize the standards, and so that the device vendors like WD have big buckets to pour our R&D into. That's all I have. Thank you.
Thank you, Dave. Amber, do we have time to take a couple questions here?
Yeah, we've got 3 questions that let's quickly cover. So the 3 questions, the first one I was going to ask to you, Ross, can any file system support flexible data placement?
That's a good question. Today, I would not say any file system. If this is just ratified and we're working through that. It can, from the point of view, if you just want to enable it. However, to get the optimum benefit, you are going to want to pass hints through. So the OS is going to need the ability to provide those hints to pass through. Hence the IOU ring stuff with Linux. In the future, I'm sure we're going to see more support for this and the ability to pass hints through. But there are benefits with that, even not passing the hints through, as Lucas showed in his slides.
Thank you, Ross. The next question is, can you specify the key parameters where flexible data placement is better than zone namespaces? I think Mike Allison and Dave Lansman both touched on the differences. However, I thought it might be helpful to have a customer perspective. Chris, if you want to offer why FDP is preferred by some customers.
Yeah, sure. I mean, this is just my perspective, but I think, you know, like Lucas said, there mentioned that the virtualization is a big one, right? Where you want complete backwards compatibility, but being able to isolate, you know, namespaces from each other from a performance, but also from an isolation standpoint, right? So that, you know, imagine if you have a mix of random and sequential at the same time, so that that sequential workload really isn't battered as much by the random thing that it's competing with. I think there's a deployment efficiency aspect of this. If you have cases where you want to reuse a drive for multiple use cases, you know, I think ZNS is more of a you sort of commit to a lowest cost sort of solution up front, but it can do that one thing. Whereas this is a standard drive, right? So you can run FTP in multiple configurations through the drive's lifetime. You can run it in a non-FTP configuration if you want to, right? And you have that flexibility over the lifetime of the device. I think the file system thing, I was just going to comment on that. I think that gets to kind of the incremental ability to do this, right? So I think with ZNS, you kind of have to have an application setting for it. The LBAs are fundamental, so your block allocation layer is just integrated with the whole solution. Whereas with a tag or a hint on the side, you don't have to redo the whole block allocation. So it is feasible to take like an ext4 and pass a hint through a few layers. Not that it's been done. Ross, I think, answered exactly correctly, but it's possible, right? You could pass that through a couple layers in the kernel, and potentially, you know, it's not infeasible that you'd be able to say, I want this file written separately, kept separate from some other files, right? So that applies, you know, maybe another way of saying that is like, if you've got log structured application, you know, that you've written it specifically for that SMR or that ZNS kind of interface from the bottom up, and that's all you're ever going to run, ZNS makes a lot of sense. Other than that, if any of those don't apply, then I think FTP is probably more appealing. And I think there's also, was touched on, the incremental aspect, right? I'm pretty happy with a WAF of 1.04, right? And there's a big cost to taking that 0.04 down to a 1, right? You have to pull all responsibility for GC to the host side, right? If I, you know, and so there's an incremental aspect of that too. So I don't know if those are just some of my thoughts on it, but it's a complicated thing, but you know, I think there's a place for both of them depending upon what you're optimizing for. So.
Thank you, Chris. Thank you, Chris. I think we're running a little low on time, so let me ask one more question, and we'll hopefully come back later in the session to the additional questions that just rolled in. So the last question, Luca, there was a concern in your slides about the JEDEC JESD 219 workload on your second slide. The concern was the minimum granularity for the workload in JEDEC is 512 bytes. However, one of the sizes you showed in your slide was 4K. Could you clarify?
Yeah, thank you, Amber. Yeah, I knew this was going to raise question, but there is a motivation behind that. So the JEDEC description absolutely require 512 byte. Not only 512 byte, by the way, it require every granularity between 512 and 4K. So I go by memory. I think it's 4% 512, 1% 1K, 1% 1.5K, and then 2 and 2.5, 3, 3.5, total about 10%. So if you want to see what is the advantage of exactly the JEDEC workload, look at the line that says 512 byte. That is it. That's the only one to look into. The reality, though, is that I don't know how much people in the audience here trace all the IOs that happen in real life, but we do benchmarking with a lot of different application, database, file system, whatever, and finding 512 byte is never happened. I mean, almost rarely. We have traced it with billions and billions of data, and if there is a 512 byte, we have to shout out, we found one. It's almost impossible. So reality is, most applications don't use it. So the JEDEC is actually very skewed to configuration that do not happen. But it is still something that people refer to. So what we did is that we got exactly the same JEDEC profile and said, what happened if we remove the not only the 512, but anything below 4K. So we align everything to 4K. And that's what we get. All of a sudden, you get a little better type of advantage because there is no read modify write dictated by 512 byte. And is way closer to reality. It's still far from reality, it's still overly pessimistic, but is something at least that we can refer to when we look to database. So in short, if you want JEDEC number, look at 512 byte. If you look something that is closer to what happened in reality, look to the other line.
Could I make a
Thank you
quick
so much.
comment on that?
Very quick.
It's important to remember with JEDEC, the JEDEC standard, that it is intended as a reference point so that we can do apples to apples comparisons across multiple vendors for endurance so that the numbers make sense. So it's not necessary. We don't have to get all cases or capture all cases. So just as a little, just remember that that's the goal of the standard. So the fact that it may not be corresponding to every workload point doesn't mean that it doesn't help us or that it's wrong.
Thanks, Dave. So with that, we have a few more questions that hopefully we'll come back to at the end, and I'll respond to privately as well. Now I'm really pleased to welcome for Grand Canyon HDD and the Yosemite V3 Flashboxes Deep Dive, Jeff.
Sounds good, thank you. Let me see if I can share my screen. Okay, can you see the presentation?
Yeah, you're good.
Okay. So hey, my name's Jeff. I'm a hardware engineer here at Meta. I'll be giving an overview of the Grand Canyon, which is our latest hard drive-based storage system, which includes a newly designed one-socket server module, which is integrated into that system, and that server module is called Barton Springs. This was recently released to the Open Compute project. In addition to that, I'll give an overview of the YB3-based flash systems, which are already contributed to OCP. Since our time is pretty limited, maybe we hold questions till the end of the presentation. Hopefully that's all right. Go to the next slide. Okay, did the slide advance?
It did.
Okay, good, great, thanks. So here you can see a picture of the Grand Canyon system with the drawer, partially open on the top right corner of the slide. Each 4OU drawer contains 2 logical storage nodes, and each node supports 36 3.5-inch hard drives for a total of 72 drives in a single drawer. Grand Canyon was designed with modularity in mind for easy serviceability and also for allowing the system components to be easily upgraded for future use cases. On the lower right here, there's a picture of Barton Springs compute module, and that's our one-socket server used in the Grand Canyon system. Server is designed to fit in the 4OU height chassis and delivering all the compute specs we needed for our desired system performance. And we'll talk a little bit more about the details of that card later on in the presentation. So what's the motivation behind Grand Canyon? The overall architecture is very similar to the previous generation called Bryce Canyon, but there are some incremental improvements that I want to highlight here. We're able to achieve a higher CPU performance, matched to what our system needs. There are some chassis refinements made specifically around system vibration and acoustics, which enable the support of denser hard drives, and I'll talk a bit about those also later on in the presentation. We're able to achieve power efficiency gains over Bryce Canyon. We wanted to maintain flexibility and modularity, but also make some enhancements. And along those lines, Grand Canyon has the ability to support both OpenRack v2 and OpenRack v3 rack types. It does take some modifications to migrate to OpenRack v3, but the changes are pretty straightforward. We've increased system modularity, which does mean more easy upgradability in the future, and it also helps support a longer project lifespan, especially as critical components go into life. So here's an exploded view of the components in the system. Since our time is pretty short, I'm not going to go into detail about each system component, but mostly what I want to highlight is that the system can be built in 3 different configurations. The first is a dual storage server. There's 2 compute nodes and 72 hard drives, and that system is fully standalone. In this configuration, all the drives are powered on all the time for faster data access. The second configuration is single storage server. And this configuration has a single compute node that's used as a head node and connected to 2 of the third configuration, which is a JBOD, which contains no compute nodes. So single head node connects to 2 JBODs, if that makes sense. and that configuration supports 216 drives. This would be our solution optimized for lowest power consumption, with a trade-off being data retrieval speed. Each of the 3 different configurations, the dual storage server, single storage server, and JBOD, have different population of the various modules in the system, and you can kind of see that in the 2 diagrams on the right side of the slide. Additional thing to highlight here is the easy serviceability of the components, where almost everything is front accessible or top accessible for easy repair installation. Also wanted to note that all the replaceable parts can be swapped without the use of tools, and the design supports hot swap replacements for the hard drives, SSDs, and the fans. So much like the rest of the Grand Canyon system, the single socket server shown here was designed with modularity in mind. So, again, if future upgrades needed to be made, the process should be pretty easy. You can see the little table here with some relevant information about some of the different critical components in the design. The photo here highlights the location of some of these components on the board. You can see the CPU, boot drive, DIMMs, PCH, and a few other things. Oops. So as hard drive density increases, the drives become more susceptible both to structural and mechanical vibration. So some improvements over the previous generation had to be made in this area. A few things to call out here in these pictures. Fan cage has isolation from the chassis by using an elastomer padding that helps reduce fan vibrations from passing through from the fan cage to the main chassis. The design accommodates options to mount fan louvers to reduce air leakage during the fan failure, and you can see them. They're kind of this, I don't know if you can see my mouse, but this green square here, this is the elastomer padding, that's the fan louvers. The idea there is that the louvers close when the fan fails, preventing air from leaking back out, and that allows the remaining fans to run at lower speeds compared to if there were no louvers installed. There were some improvements made to the honeycomb pattern on the back of the fan cage to allow better airflow. The design implements acoustic phone installation at strategic locations. They're not shown in these pictures, but it was kind of placed close to the last row of the hard drives in the system to help dampen some vibration. The drive plane board, that's the board that all the hard drives plug into, has air gap seals to help reduce air leakage. And in turn, that helps the fans run at lower speeds, which causes less vibration. So you can see in the middle picture here, there's some arrows here pointing to some of those air gap seals. Some improvements to the fans themselves were made, including a lower fan blade count and tuning the geometry of the fan blades to help vibration. Let's see, and the system design accommodates drop-in replacement of a new hard drive latch. You can see that here in the bottom right-hand corner, and one option is to make that out of a stiffer material, which can help reduce the transmission of vibration to the hard drive. In the middle here, there's a photo of this aluminum chassis, and basically it's an example of an acoustical and structural surrogate that was used to characterize the vibration in the system. The surrogate is basically a hard drive size chassis that with microphones and accelerometers in it to make some measurements. And in parallel, we also work with hard drive vendors to help with the structural characterization to compare the benefits of all these different vibration mitigation measures we put into the chassis design. So this slide is references for all the contributed info and specs for Grand Canyon and Barton Springs design, as well as some information about acoustical surrogate design and the OCP workstream for that acoustic surrogate. So if that's something that interests you, please do take a look. Feel free to reach out to those groups if you do want to participate. So here, this is the YV3 flash. On the upper right here, you can see a picture of the Yosemite V3 system. We abbreviate that YV3 in 2 different configurations. They're both considered expansions of the Delta Lake one-socket server design that uses the Intel Xeon processors, codenamed Cooper Lake, and supports up to 88 watts of power and 26 cores, making this system pretty power efficient. The platform's highly modularized system built with U1.S drives in mind and includes components such as server boards, expansion boards, baseboard, power modules, cooling fans, and they all fit into a 40U cubby chassis. In the picture shown here, Vernal Falls is the design on the left, and Sierra Point is the design on the right. And we'll get into some of the details about the systems in just a couple of slides. And just a little about the YV3 modular design. The YV3 chassis has is broken up into 3 cubbies, and each cubby accommodates 1 sled for a total of 3 sleds per chassis. Hopefully that makes sense. You'll see in future pictures too. You can see the sleds are 4 OU height and sort of looks like those square outlines for each section of the chassis. From there, each sled can be broken down into blades. So for example, on the left-hand chassis, you can see there's 3 sleds with 4 blades each. And on the right-hand picture, you can see there's 3 sleds with 2 blades each. So yeah, I'll have a more detailed view on the next slide. But also here are the contributed specs to the OCP website. So I'm not going to go through each of the system components in detail here since our time is kind of limited, but feel free to read about these, in those OCP specs linked in the previous slide. I'll touch on some of the high-level info though. The YB3 system sleds and blades are front access designed for easy accessibility and maintainability. All replaceable components are removable without the use of tools to make DC data center repairs easy and fast. For Sierra Point on the left, like mentioned in the last slide, the chassis structure is broken down into 3 cubbies. Each cubby has 1 sled, and each sled can accommodate 2 blades in each sled, so totaling 6 2OU blades per chassis. The picture here on the left only shows, one of those blades installed, and another one can fit on top of that 2OU section. So what does that mean? This means that up to 3625 millimeters height heatsink E1.S SSDs can be supported per chassis, and that would give a total of 576 terabytes of storage. If we wanted to fill an entire ORV2 rack with these 2OU blades with 8 chassis per rack, we get a total of 48 servers per rack. For Sierra Point, each server has its own OCP NIC to deliver data traffic to and from the server. And this configuration is typically most well suited for storage type applications and is usually paired with a higher capacity E1.S drive. For the vernal falls on the right, as mentioned before, the chassis can carry 3 sleds with 4 blades in each sled, totaling 12 1OU blades per chassis. So this means 48 25 millimeter heatsink E1.S's can be supported per chassis, and that'll give a total of 768 terabytes of storage, a maximum of. So if we wanted to fill up an entire ORV2 rack with 1OU blades, 4OU systems can carry 12 blades, so the entire rack is 8 chassis, so you get a total of 96 servers, making the system a high-density rack for hyperscaler data centers. All blades in the vernal falls cubby share 1 multi-host OCP NIC, which helps eliminate some of the network cabling. And this configuration is typically, most well suited for compute type applications, typically used with lower capacity E1.S drives. Both of these platforms allow for flexible compute to storage ratios, support high density, have excellent CFM per watt, can support hot plug, and support device presence detection, perhaps for security purposes. Here's a block diagram of the vernal falls expansion board on the left side. It covers things like PCIe interfaces, I2C, clocks, powers, and a few other things. One notable item is that the interface to the E1.S drive on the system are PCIe Gen 3 by 4 links. And on the right side, you can see a view of the PCB itself that connects to the Delta Lake server card using the 4C and 4C plus connectors. And you can also see here also where the 4 E1.S SSDs plug into the card. So here's a block diagram of the Sierra Point expansion. Like the previous slide, it shows high-level interfaces, I2C, clocks, PCIe power, and a few other things. Like the vernal falls, each drive gets a PCIe Gen 3 by 4 link. And on the right side, you can see a mechanical view and also a kind of a quarter-turn perspective view of the PCB. It's a little bit small, sorry about that. Some of the electrical connections are made through the 4C and 4C plus connectors to the first OU, we'll call it. And then some of the electrical connections are made through a riser card that connects to the Delta Lake board through an expansion connector. You can see that connector here in the diagram, under the mechanical view, kind of where the 2OU expansion hangs over the 1OU on the right side here. Hopefully that's clear. You can also see the location for the OCP NIC on the bottom of this, the 1OU system in the front here in this rendering. So, as mentioned earlier, this design accommodates 6 25 millimeter heatsink E1.S drives. Okay. And then here's a reference page with all the relevant information about these designs. The design collateral for the Grand Canyon design, as well as the Barton Springs, should have been released. I think Delta Lake Server, Vernal Falls, and Sierra Point expansion designs were released previously. So do feel free to check out those for any further reading details. There's a lot of good information there. So that's all I have for today. Not sure if there's any questions, or maybe we hold it till the end, whatever works.
There's two questions, so let's cover them briefly, Jeff. So how does Grand Canyon help longer deployment, and how have you qualified it?
So there's several things that we've done in the design, right? So it's very modular. So the Barton Springs CPU card is self-contained. The NICs, the E1.S slots, all those things are individual modules. So if, say we wanted to increase, if we deployed with a 1 terabyte E1.S and we wanted to go to 2, we could do that, right? We've done validation for, higher powers or those sorts of things. For example, on the NIC, the OCP 3.0 NIC, we designed it with a by 16 Gen 3 interface, but for our first deployment, we're only using by 8, right? So what that does is allow, say we had a future use case where we wanted to increase to 100 gig NIC, for example, we could do that. Same thing with our storage controller card, right? If parts go end of life, we have the ability to replace just those particular sections, and that in turn extends the useful life of the platform.
Thanks, Jeff. And the second question is there a specific reason that you're using a JBOD for the system?
So what we do for our JBOD portion is that's what we try to do is we use that in something called cold storage, where it's optimized for low power. So what we try to do is remove everything we can out, and it's and turn off as much stuff as we can. We're not too worried about how slow it is to retrieve the data. I mean, we are, but it's less sensitive, right? So the goal there is to eliminate as much power. So the CPUs generate quite a bit of heat. So that was kind of the motivation behind that configuration.
Awesome. Thank you so much, Eric. Thanks for the great presentation.
Yeah, thank you very much.
Next up is the regulatory environment for storage. So welcome, Eric.
Thank you. And let's get the screen set up here. With a little luck, I'm sharing correctly.
We see it, and if you turn on your webcam if you can, and we'll be off to the races.
Oh yeah, show my ugly mug. All right, hopefully that works.
You look great. Thank you.
All right, to quote somebody famous, now for something completely different. So my name's Eric Hibbert, and I'm with Samsung Semiconductor, but relative to this talk, I chair the U.S. activities around cybersecurity and privacy standardization, both at the international level and within IEEE, which means I tend to track the regulatory space fairly carefully. So I'm going to give you some of my insights into what's going on from a storage perspective. All right, so I've broken these up into a few categories to make it maybe a little more consumable. So first up is privacy. This tends to get a lot of attention because well, in short, the data indiscretions here can be extremely expensive, as in terms of measured in percentages of your annual take, especially if you're in Europe, but it's not limited to just Europe. US has HIPAA. Most countries at this point have some sort of privacy data protection regulations in place. This has a trickle-down effect to storage. It may not explicitly call it out, but what it does do is identify the kinds of data that need to be protected, and this can vary between personal information to personally identifiable information to healthcare records and things of that nature. The regulations in this space tend to cover things like disclosures, which is essentially how you're going to use the data that's being collected, how, where, why you are collecting this, how you're processing it, how you're storing it, which is the piece that's relevant to the storage industry, whether any anonymization or encryption are required, or whether those give you safe harbors. safe harbors in that the lawyers don't give you a call if there's an issue. One of the challenges is that some of the regulations are written in terms of reasonable security. We are seeing some trends moving to risk-based. The reasonable security, as I'm fond of joking with some of my friends in the American Bar Association, is whatever a good New York lawyer can argue is currently reasonable. It also means that that bar is shifting continuously. So as new specifications come out, new standards come out, that bar can shift on you. And again, so this requires you to sort of pay attention to what's happening in the privacy regulation space. Another facet that comes into play is retention and destruction. So in some cases, you are required to eliminate data after a certain period of time. On the flip side, for example, I live in California, and in the case of mammograms, if you have that kind of data, you are never allowed to get rid of it. So you've got both sets of problems, which again presents some challenges to the storage industry and those who use the technology. And last but not least is breach notifications. This is basically the US contribution to the privacy arena. We taught the world that pain is achieved by forcing organizations to do these notifications because they're very costly, very pain in the butt to basically do. And just about everybody has adopted this mechanism. You would think, moving on to confidential information, this is sort of the security side of the house, that there would be all kinds of regulations in terms of securing data. It turns out not nearly as much as we see with privacy. Privacy is the 300-pound gorilla in this space, but there are regulations. For example, Sarbanes-Oxley has some elements that are dealing with data retentions associated with public companies. Another example is the Espionage Act, again, in the US, dealing with trade secrets. So this is an example where there's a requirement to basically protect this kind of information. The interesting twist on it is if you haven't actually made reasonable attempts to protect it, then you may have some difficulty actually demonstrating that it's a trade secret. If you put your favorite recipe on the web, even a not so effective lawyer would be able to sort of blow that out of the water. Another one, if you're doing work with the U.S. government, is FISMA, and this gets into lots of government data, even beyond classified information. So there's a whole regime on anything that's considered sensitive, for official use only. And if you happen to be using or housing some types of US government data on non-government systems, you will find that there are some stringent requirements that have to be met in that space. Another facet that we're seeing, this is becoming more and more prevalent. It's data sovereignty and localization. Think of the sovereignty piece as government policy or law that's asserting that a certain kind of data falls within their domain, needs to be protected. It usually is sort of a geographic location. There's definitely some examples here. The Australian privacy principles are requiring personal data to be kept in Australia. GDPR in Europe, General Data Protection Regulation, is mandating data protections for personal information. This one is interesting in that what it considers personal information is not intuitive for most folks in the US. For example, photographs, images. If you don't have permission, if you've taken a photograph of somebody and you're posting it, you may in fact be in violation of GDPR. And again, we're seeing most countries are looking at data sovereignty requirements. A lot of this is coming out of the advancement of cloud computing technology and its rapid deployment and use. It's to the point where many cloud service providers are having to look at where they site their data centers to basically deal with some of these requirements. Data localization, again, this is dictations on where you can put the data. Again, GDPR, 300-pound gorilla here in many ways, currently encourages data to be hosted in the EU or specific countries. With that said, we're seeing that Germany and France have actually gone a step further and are now set some country-specific requirements on top of that. And there are others, for example, US, Canada, India, China, and Russia all have some form of data localization kinds of requirements that exist in the regulations and the laws. The next area from a regulatory landscape perspective is the circular economy. This is a new and emerging area. It's definitely one worth keeping an eye on. We're seeing, again, the Europeans have regulations out. Hopefully you're aware of the EU Lot 9, as we call it, codename Green Servers, Green Storage. It has an interesting feature in that you are required to include secure data deletion functions as part of encouraging reuse. It applies to if you're selling servers and storage into the EU with between 400 and 400 drives. This definitely applies to you. They've exempted enterprise, what they call enterprise storage kinds of mechanisms from this. But these days, that covers quite a bit of technology. We're also seeing that the U.S. Securities and Exchange Commission is beginning to operate in this space, and the issue that we're seeing right now is one of reporting for public companies. So they're being required to disclose information about the direct greenhouse gas emissions, indirect emissions from purchased electricity, other forms of energy, and emissions from upstream and downstream activities. Think of this as the value chain or supply chain. So you're buying things that essentially add to your carbon footprint, if you will. This is definitely getting attention because first step is reporting. One can imagine that in the not too distant future, if it looks like things are going in the wrong direction or not going and not improving, that we could see follow-up regulations that will put some teeth in improving that situation. We're also seeing that the EU has got a carbon neutral circular economy by 2050. If they follow suit with what they've done, for example, with the General Data Protection Regulation, as a model, then we should anticipate that, again, there's going to be some level of teeth in that regulation at some point. Areas of interest, green claims and labels. So there's a lot of misinformation that's floating out there, and it looks like we're going to see some actions in that space. Another area to pay attention, especially if you're a vendor, is the right to repair. So those are two arenas where we're beginning to see some chatter in the regulatory space. And of course, there are these sort of other things that you have to sort of keep an eye on. So if you're dealing with payment cards, there's the Payment Card Industry Data Security Standard. This is not a regulation. It's not a law. It's worse. It's actually a contractual clause, and it has some pretty significant teeth. An organization that violates some of this could be fined in the hundreds of millions of dollars, or lose their ability to process credit card transactions, which could be devastating in current state of affairs. So when the PCI DSS makes adjustments or the audit criteria is adjusted, that tends to get attention. And there are some flow downs that, again, indirectly affect storage ecosystems. We're seeing, again, in our friends in Europe, some movement to deal with cybersecurity certification frameworks for digital products. There was a recent update to common criteria, which is ISO 15408, which has been used for security certification of products over the years. We're anticipating that in the not too distant future, that products being sold into the EU may actually need to have this kind of certification. So there's a bit of movement in that arena. And then the NIS directive that is fairly new, January of 2023. So looking at a high common level of cybersecurity across the EU and harmonizing EU approaches to incident notifications, security requirements, and supervisor measures and information sharing. So yet more on the way. This is fairly new, not a whole lot of discussion about it yet, but we anticipate, again, sort of a trickle-down effect. So just to bring this up to a close, sorry for the whirlwind tour, but I think the takeaway here is that there aren't a whole lot of regulations that are directed to data storage explicitly, but there's an awful lot indirectly that do impact storage and storage technology. One of the biggest problem areas is guarding against data breaches due to loss of control. So this is something as simple as drive removal. You hand it off to a third party not paying attention. You didn't take steps to clear the data. You have an instant data breach. That loss of control, in many cases, constitutes the basis of a data breach. We're seeing data rest encryption and storage sanitization are sort of critical elements of that. In fact, a lot of the sanitization is taking advantage of the encryption. And the other piece is that we're seeing more and more risk assessments being required, whether it's from the privacy side or from the security side. And storage is now being subjected to that. And there's even an ISO standard dealing with storage technology that is now part of the ISO 27000 series, if you're familiar with that. All right, so there's I mentioned the ISO 27040 is the ISO standard. There's a couple other documents in the NIST. And if you're interested in requirements around media sanitization, the new IEEE 2883 is something you probably want to pay attention to. So that's what I have for you today in terms of what's going on in the regulatory space. As you can tell, some of it's a bit fluid and complicated and involves lots of lawyers. So I think I'll stop there. Hopefully, if there are any questions.
That was excellent, Eric. Just one question. If you had a particular call to action for what we should be working on in OCP storage across this smorgasbord of items, what would it be?
I think, looking at what OCP is doing with things like OCP, the attestation and measurements in that space, we're basically trying to improve the overall platform security, if you will. So it's storage as well as how it interacts with. I think continuing those efforts is going to be helpful. It helps guard against malware. The issue we've got to be looking forward to is how do we make sure these are covered if certifications, security certifications become mandatory. And that's where some of the crosstalk between what's happening in the formal standards and organizations like OCP are valuable.
Thank you so much, Eric. Thanks for the great talk. Now we have Steve Wells is going to talk to us about enhancing fleet health monitoring opportunity, leveraging OCP's Datacenter, NVMe, SSD specification, standardized telemetry. So take it away, Steve.
Okay, guys, can you see me, hear me, and see the display?
Not yet.
No one can see.
You're waiting to view Steve's screen. Eric, you can go ahead and turn off your camera. And there we go. Now we're seeing your screen, Steve, and we're just need to see your face.
I thought I had that turned on too. Okay. How about now?
Perfect.
Okay. Hey guys, and thank you. I consider it a real privilege to be able to talk to you guys about some of the future telemetry standardization that we're talking about and why we're doing it as part of the next release of the OCP Datacenter NVMe specifications. I've worked with many of you guys before. I'm Steve Wells. I'm a fellow, and I work in storage solutions architecture over at Micron. Okay, so what are we talking about today? So the current solution for how we do both monitoring, and I would argue monitoring, predominantly health monitoring, but there's also other kinds of monitoring we'll discuss in a bit, as well as the debug. So today there's multiple standardized smart pages, which means you're going to have to probe multiple pages to get a complete picture of for monitoring. There's no opportunity for anything vendor unique inside of the smart. Both sets of smart pages require that all remaining fields are reserved and shall be set to 0. And OCP has an additional requirement around SEC 19, does not allow vendor unique log pages outside of the specification. So this pretty much says that you can have a one-size-fits-all sort of telemetry or monitoring strategy today. And then they extended it by talking about, well, there is the NVMe concept of telemetry host and device telemetry pages, but and Telemetry 5 says data area 1 shall be used for monitoring, but really offers no payload guidance. And in the header of the telemetry page is something called reason identifier. It's 128 bytes, and there's really no guidance on what the payload for that needs to be. So you end up with anywhere from ignoring the reason identifier to having nothing but vendor unique data in there. And then finally, to Eric's presentation prior around privacy and confidentiality, there's really no guidance on what constitutes for requirement SEC 22, this human readable requirement on the log page decode. So for today then, we have requiring monitoring requires multiple IOs. Debug is vendor unique, and various interpretations of what it means to be human decodable, which is what the new standard is working to address. So I'm going to start with a quick analogy, and I'm by no means an expert in this space, other than maybe an enthusiast, which is here's an example of a VU extendable monitoring and debug solution from the automobile industry. If I plug in my hybrid electric, I get different telemetry than I do when I plug in my older gas engine. However, it is based on some standard for which a standardized reader can be placed in there and data can be brought out. So what are we trying to do here as part of the NVMe standardized telemetry? We're going to standardize the telemetry in data area 1 and 2 from the NVMe spec, as well as standardize the payload of the reason identifier. So to start with, data area 1 is going to offer low latency single command fleet monitoring. It's strictly data area 1. It does map in the other useful smart pages of data. It allows some additional standardized statistics that help both with health monitoring as well as load balancing opportunities. And then beyond that, for almost every one of these types of statistics, there's also an opportunity to insert vendor unique statistics, as well as to create these event FIFOs with some capabilities in a standardized way. So this offers you a one and done fleet monitoring. And then post-panic, post-crash, there's going to be additional area in data area 2, as well as the populated reason identifier. And I think the reason identifier is good for segmentation. If you have many fleet failures you're looking at, you can segment them out with luck and good coordination. I think the reason identifiers will be really good for segmentation. So, and then finally for this thing, we're gonna offer a single open source OCP NVMe CLI. And this will allow decoding in a human readable format that supports the SEC 22 requirement of being human readable. And what's interesting about this is with a single industry standardized OCP NVMe CLI plugin, it'll allow what's called the telemetry string logs. And this allows you to then give human readable identifiers for vendor unique statistics and events that you might put in there. So, just to offer some view, at least Micron's view on this, there's going to be a region of standardized human readable decodable regions in data area 1 and 2. That doesn't prevent data area 3 and 4 to potentially have some vendor unique logs and worst case physical access to the drive for the, and the goal is that we're catching the preponderance of whatever issues that we're dealing with in a fleet situation with the standardized telemetry tool, but it does recognize that that's probably going to be nearly impossible to get everything that you might want into data area 1 and 2 exclusively. So building out on this then, if you're in a monitoring mode, effectively you can read data area 1, and then the OCP CLI tool can read data area 1 as well as read the vendor unique string decode log pages, generate a human readable output, and then before being released to a vendor for analysis, it allows a data center security inspection. So I think this is the motivating reason why it was human readable in the first place, is to where Eric's comments were, we don't want to be leaking privacy or customer confidential data, and this gives a chance to confirm that. In a debug scenario, you would not only read data area 1, but you would also read the data area 2 and the reason identifiers, effectively doing the same thing with the OCP CLI telemetry plugin and the vendor unique string decode offered by the drive to allow a human readable output that can be brought to security inspection and then sent to the vendor for analysis. So a little bit more detail. The way the spec is structured, it addresses both host and device initiated and makes a request that it actually reports the same data, both host initiated and drive initiated. Things that are human readable are in data area 1 and 2. The low latency for monitoring is data area 1 and the headers. And data area 3 and 4 are not specified but not denied either, and this would be for always available decode or always available non-decodable, as in doesn't the OCP CLI tool won't help you debug in this decode in this space. But it's also an expectation this is high latency. The only thing that's is low latency is the monitoring in data area 1. And then potentially our assumption is there's going to be, at least in our view of it, there'll be data area 4 data that's always available, and then data area 4 data that potentially would only be available after a crash debug or a crash event has happened. And this is where the crash dumps would go. So to benefits and calls to action. So it's an open standardized decode via the OCP NVMe CLI generated human readable debug output. It's good for the security inspection. It does fully clarify the requirement of debug needing to be human readable, which was the existing SEC 22 spec is now clarified as what does it mean and what's the scope of that. From monitoring, it's a single IO event that's issued periodically for all reads. It's low latency. It enables vendor unique attributes to be inserted in a standardized way. It facilitates the data center and vendor to collaborate on fleet health monitoring, and by adding to allow not one size fits all monitoring, but allows to have specific architectural elements of a vendor's architecture to also be included in that health monitoring. I think this is going to be powerful. And then finally, the host can monitor their fleet utilization for load balancing purposes, and there are several standardized statistics in the spec to help with that. For debug, obviously improves time to debug, faster segmentation, and time for vendor to get this data. And this is going to be a big deal, is this faster turnaround time around debug. So calls to action. Call the authors on this call, please. Contribute the OCP NVMe specification and the OCP NVMe CLI decode tool. And call action to the drive vendors is to incorporate standardized telemetry into your new SSDs. And we encourage vendor unique data to be included in there for more productive monitoring and debug. And as the OCP NVMe CLI decode tool project is out there, be sure to test against it and offer your any sort of improvements and or bug reports into that. And that is all I had.
Awesome. So one question for you, Steve. Great presentation. Regarding the, is it possible to quantify high versus low latency?
Darn good question, and I don't think it's terribly clear on that. I think the guidance from the OCP spec is that it needed to not have a meaningful impact to IO latency. However, the spec does not come in and specify to any great detail exactly what a low latency impact event would be. And Ross or Lee, if there is anything in there, I can be corrected. But in general, I think the suggestion, just like SMART is it needs to be a low latency event and not impact other IO in flight.
Okay, one more question and then we'll go to a break. Will this telemetry ever get support over NVMe MI?
It's a good question. And I think at minimum, it's going to come down to can MI do telemetry reads? And there may be other people on this call that may have more detail than that, but effectively, this is all that's required is to snapshot the telemetry.
Well, thanks so much, Steve. We wanted to give everybody a quick coffee break, so or whatever beverage you would like in your geography. So if we could resume in 5 minutes at 10:45 a.m. Pacific time, we'll see you guys shortly with the update on the device specs.
Okay, I hope you all had a good break. Next up, we have Lee Pruitt at Microsoft and Paul Kaler at HPE. Paul is going to talk about the SATA device spec, and Lee will talk about the data center NVMe spec. And with that, Paul, you want to take it away here?
If I can unmute, here we go. All right. Yeah, Lee, it looks like we're maybe zoomed in again. We may have to go out of.
Oh, let's see here. Tried to do the whole screen. Hopefully that would work.
Yeah, you can just shrink the side of the left. Yeah, there you go.
All right. Bad presenter, no builds for you.
It's all good. It'll work.
You can, yeah, if you shrink the ribbon bar up top, right, it'll make that a little less busy. But click the caret on the bottom right.
That back to.
Oh, that works. Yeah.
Great.
All right. So I guess go up one slide here and.
All right. There we go.
All right, so I wanted to thank everybody for being here today. I'm going to talk a little bit about the OCP Data Center SAS SATA spec and give you an update and kind of an overview. As Ross mentioned, my name is Paul Kaler. I'm a future storage architect for HPE. All right, Lee, next slide. All right, so I want to first kind of set the ground with some of the challenges of the current approach of getting SAS and SATA devices out for customers. We're all very familiar with the industry specs that we have today. They're very feature rich, right? So we've got the T10 and T13 and SATA IO specs. Lots of great optional features in those specs, but unfortunately that also creates some problems, right? Because then we wind up having different implementations from different suppliers, and that leads to products with inconsistent capabilities across the landscape. And what we really need to know is, right, what do data center customers require of those industry specs? And unfortunately today, up until today, there's been no open public customer specs for SAS or SATA devices. We all have our own kind of confidential specifications that we share with suppliers. Of course, this limits industry innovation because you can't really collaborate in the industry when these are confidential specifications. And this winds up generating a ton of extra industry work with very limited value at the end of the day. And then when it comes to testing, right, you have all these optional features in the industry specs. But again, if you don't know what is really required by a customer, you have to create this big superset test. You don't really know what needs to be tested. So you maybe have a very bloated test suite. Makes it very challenging to have a good focused test suite. So all this lack of collaboration really winds up slowing innovation. So Lee, next slide. All right, so basically we all got together, Microsoft, HP, and Meta, and I think most people here are familiar with this. We've gotten together and merged all of our requirements for SAS and SATA devices into a single spec. I think I shared last time at OCP Summit that we now include both hard drive and SSD requirements in this spec. But the big news that I was excited to share, right, is it's now been contributed. So as of yesterday, actually, so hot off the presses, right, just contributed officially version 1.0 of the spec. Microsoft, HP, and Meta have got it out there. And so we're all very excited to finally have that contributed. You can see the link below, or if you go to the OCP contributions site, you can see the database there. That's the first one in the list, actually. All right, next slide. All right, so I just want to talk a little bit about some of the benefits of doing this open spec. I think most people understand this, but it's kind of good to kind of touch on some of the key benefits we see this providing for us. So clearly confidential requirements, I think everybody understands that there's trade-offs because you have limited resources in the industry. And so when you get these specs from different customers, you've got to have siloed teams, and all those confidential requirements mean you can't pool your resources very easily. So if you look over to the right, this trade-off triangle, I think most people here would be familiar with this in product development. You typically have your features, quality, and schedule, and you can really only get 2 out of those 3. And so we often hear from suppliers, you know, we have a specific schedule we want to launch a new drive with, and we have all the features we want supported. And we often hear, well, if you want to hit your schedule, we're going to need to drop this feature, right? So there come your trade-offs. Well, with an open requirement spec, we're really hoping that the industry can consolidate resources down and reduce a lot of the trade-offs they have to make, because now they're focused on one spec for most of their customers. Of course, a key component for this is that this common requirement spec really needs to be across multiple large customers, so that you can take a lot of your work that was individual and group it down into a single work stream now. And so the goal, of course, is to get more features, better quality, and faster time to market. So now you get all three of those aspects without trade-offs. Next slide. And to talk about one of the key benefits that we see with that reduction of resources is kind of focused on firmware, right? So getting to a common set of features means that we should have fewer custom firmware branches in the industry. And we've talked to vendors at different times, and they often have to support more than 10 custom firmware branches just for all their different customers because they have different requirements. Clearly, that's going to lead to lots of inefficiencies. They have to have redundant resources to develop, test, and maintain all those different firmware branches and codes. So our ultimate goal with this spec, right, is to get to one firmware build, kind of the one firmware to rule them all for all of the functional features it includes in our spec. And so that, of course, will allow more suppliers to focus all of their resources on just developing that one firmware. That should improve their product development and hopefully reduce the overall costs on the back end of developing these drives. We do still support, even though we have one firmware, we still support the ability to have build time customizations via device profiles. But in the SATA spec, if you guys are familiar with the NVMe spec, we had a handful of device profiles for the different configurations. We've been able to narrow this down to just one in the SATA spec, which is basically whether it ships 4K or 512 byte native from the factory. So we still have some ability to do customization there at build time, but it makes it very leverageable for the one firmware. And again, driving it home, right, more features, better quality, faster, and hopefully less costs in the future moving forward. Next slide. So let's talk a little bit, circle back to testing, right? So testing is tough when it's all confidential, but with published requirements, now you have open source requirements that lets third-party test providers really develop a very comprehensive test suite, but on very specific features that the customers actually need. So they don't have to have this big bloated test suite that may have a bunch of features that aren't even used, so they don't have wasted effort developing that. That reduces their burden of maintaining either multiple custom test suites for different customers or a very bloated test suite, which should help reduce their cost and development time while greatly improving the quality of the test suite they can put out with focused test patterns. So customers and suppliers both now can reduce our own test and validation costs, right? So now we can repurpose some of the internal test development teams over to our product development, which is really what we all want to be doing to begin with, right? We don't want to be testing internally if we don't have to. If we can use third-party tests, that's much better. Again, driving home, right, more features, better quality, faster, and less costs is the goal of all of this. Next slide. All right, so real quick to talk about what's in the spec. Basically at a very high level, it's everything that you need to know to build a data center SAS and SATA hard drive or SSD for a data center customer. Some of the topics that we include basically are SAS and SATA interface requirements, what you need to do for power and reliability, performance requirements, environmental specs, security requirements, labeling and compliance, as well as sustainability. And all of those requirements are all sorted by their individual ID numbers to cover all of them. So it's very easy reference, and you can test to those specific ID numbers. So it creates a very easy way to go and reference the spec and all the requirements within it. Next page. All right, so a couple of examples of the interface requirements. Basically, there's existing T10 and T13 specs. So we specify which revisions of those specs, what's the latest version that you need to support for the SAS and SATA spec. We go through those specs and we define all the mandatory and optional features that are within them, the log pages and the commands as well. Some of the requirements we specify out in the PHY and the link and the app layers as well. Some of the general configuration and operational requirements that we specify in the spec are how to handle write cache management, firmware download, which commands you need to support for that, error recovery, SMR configurations, interface speeds that need to be supported, and how to handle background activities. Next slide. All right, some of the performance and reliability examples that we cover in the spec are data center performance metrics, where we cover latency, IOPS, and bandwidth for different data center workloads. We cover the MTBF and AFR requirements from 2 million to 2.5 million hours. Those are based on different workloads, temperature, and humidity. Some of the reliability metrics that we cover are load and unload cycles, how to handle sudden power loss, data integrity requirements, that includes Uber, and head degradation requirements as well. And I think that takes us to you, Lee. All right.
Great. Thank you, Paul. So I'm Lee Pruitt, Director of Cloud Hardware Storage at Microsoft. So doing lots of work in standards and SSD development for Azure. And so today I'm going to talk about what we've been working on since version 2 of the OCP Datacenter NVMe specification, which we're now calling v2.5. So kind of thinking back along the 3-4 years now that we've been doing this, kind of a long, strange trip. OCP 1.0 was about 72 pages. Then we almost doubled that in OCP 2.0 to 127 pages with lots of new requirements and capturing good information. And now currently we're about 235 pages for the new spec. And basically down here it's like, you know, if we double again and we surpass the NVMe base spec, well, I think I'm going to retire. I just need to get out. So why has the dock nearly doubled in size? Frankly, I think Steve touched on it very well, or delved into it deeply very well. Debuggability, all the new stuff around the new definitions for telemetry, and some other stuff around that as well, some TCG history and things like that that I'll get into later. Obviously, security. We've added a whole bunch of new requirements for security, some new use cases, putting in things for Ross's FTP and Google as well. Some things around, you know, we always find things in the wild, and so once we see those, we want to try and figure out how to plug those holes, and clarifications and bug fixes. And so kind of looking at this, the majority of the work is kind of the big stuff, where we're going to smaller stuff as you go down this page. And so to kind of delve into that to the next level, we'll start actually from the smaller stuff and build back up. So things around clarification and bug fixes. You know, frankly, a lot of this is questions from vendors, i.e. we thought we'd written the requirement clearly. Obviously we hadn't, because if different people are asking different things about it. And so we're trying to clean up language to ensure that when somebody reads it, everybody comes to the same conclusion. Same frame from testers. Frankly, testers are one of our best beta people for doing work on the spec, because they're actually implementing tests against the different requirement IDs. And so when they need clarification, that's a very clear indication that we need to clean up the language. Another one is from frankly, our internal engineering groups, trying to understand, you know, once we have a requirement, they may have asked for this requirement, and then when they read it, they're going to ask questions about, well, is that really, I'm not sure that's what I really meant when I told you to put this in. So how do we get that cleaned up? And best of all, feedback from OCP storage folks like yourselves. So all of that's been very helpful as we work through and add to the spec. So kind of things around issues found in the fleet. It's a little bit of the same vein as the previous, but it's again around interpretations. So mismatches in interpretations between what we had in the spec and then what the engineering group or the use cases in the fleet once we get there. So making sure that once we start to test this stuff in fleet, how do we ensure that what we expect for the devices is what the engineering group is going to be able to use in their use cases in production. And then other things, what we find is mismatches in implementation. So we had it down there in the spec, but one vendor implemented it a certain way and another vendor implemented it a slightly different way. And so how do we make sure that that's clarified so that we can get one implementation to rule them all? And of course, the bane of all of us escapes, i.e. something that we didn't think about, a hole or a seam in the spec that when it, at scale comes out pretty quickly, and is something that we need to figure out how to plug. So around new use cases, specifically, we've added a flexible data placement requirement section. And really what that's done is this is the first time we've ever to do this. We'll probably be doing more of this in the future with if implemented requirements. So things like FTP, ZNS, other future use cases. So not necessarily that this will be a one all across the board has to be implemented, but for certain use cases and certain supplied base, those will need to be implemented in the way that we specify here in these implemented requirements. So security, there's about 27 new security requirements. As we all know with security, it's never ending. It's a journey, not a destination. As threat actors change and advance, we have to try and keep up. And so there's a bunch of new stuff around that. Basically, a lot of what we did here was we're trying to match and keep in parallel with the SATA SAS spec and the boot specs. And so in the future, this you can see where if we can keep this all in parallel and common, we may actually want to pull that section out and make its own spec so that the other specs just reference it and it can evolve on its own. So debuggability, that's the big one. Some things around that, we've added things around the current TCG state of the device. We've actually had a kind of a TCG security audit log. So in TCG history, what's the history of the device been? And of course, the big one, telemetry. So this has kind of been done in a way that's hopefully flexible, extensible, and human readable. So I think Steve went through this in great detail, and so I don't need to harp on it too much, but in the sense of this way, again, we can streamline that debuggability, streamline how data gets aggregated at scale in the fleet and gets driven back through conduits back to each supplier. So each supplier gets their telemetry data in a highly efficient process so that we can very quickly find problems, debug them, find emergent problems, and that sort of thing. So with that, thank you.
Thank you, Lee and Paul. Great talks. So, Paul, what do you see as the biggest challenge when you look at the SAS SATA specs, or the biggest pain point you're solving? And we cannot hear you.
Help if I came off mute. Yeah, so I think it kind of goes to the same kind of point of getting devices that basically support the features we need and the time and the schedule that we want. So I think going, to a shared specification, we're hoping helps a lot with that, and getting to a point where we can get all the features we want in a timely manner, and also really with better quality as well. So I think, for us, that's the biggest pain point we have today is, trying to get all the features in, and then it doesn't meet our schedule, or we maybe have some even quality issues, which is really bad. So we want to try and get to a point where all of those things come together and we can get everything that we want. So kind of want our cake and eat it too.
Sorry, it was giving me a hard time because I'm supposed to show my screen next. So, Lee, any big pain points you want to touch on the NVMe spec, or what's beyond 2.5 in your point of view?
Yeah, so I think pain is relative. So we're busy here as each of these revs of the spec come along, we kind of find new pain points that need to be addressed. Debuggability and security always being one of those around that. And so, I think we're going to go with the telemetry definition here. We're going to go a very long way in helping with that. I'm sure once we get this kind of implemented and in use, we'll find new things to have to work on to help with that. So I at this point, don't have anything like huge and obvious that we want to put into the 3.0 or v.next, whatever you want to call it. But I'm sure those will be coming at some point.
Yeah,
Okay,
One thing I might just add to that real quick is, I think one of the differences between the SAS and SATA spec and the NVMe spec is the specs that we base them off of in the industry, right? So SAS and SATA are pretty mature. There's not a huge amount of changes going there. So it's really trying to get, again, that consolidation and getting all the features we need from the specs that exist. I think for the NVMe spec, right, we probably don't know what we don't know yet. And I think that's really going to be the future stuff that we put in. Is NVMe is a very dynamic spec itself. And so as it adds new things that are optional, then we want to call those out in our data center NVMe spec. So I think that's probably what I see as the future is, more things that get added to the NVMe spec that we then want to call out specifically, whether they're, especially when they're optional, because then we want to specify whether we need them mandatory in our spec.
Great point. And live migration will probably be a great one for that.
Right.
Yeah, for those not following NVMe closely, there's a live migration technical proposal being driven being championed perhaps by Google and Microsoft. So stay tuned for that. Last question, SATA, current save internal state data and NVMe telemetry host controller are very similar. Any OCP intentions of convergence?
That's a good question. I don't think that we have talked through. We do try and keep as much consistency as possible between the SAS SATA spec and the NVMe spec where applicable, and that may be a good one that we need to look into and see if it would make sense to look into that. Yeah, that's a great question.
Well, thank you both. So, and thank you in advance for participating in the next, our last update, which is we're talking now about customer problems and requirements panel. So I'm going to kick us off. And I believe everybody hopefully can see my screen. So we're going to talk customer problems and requirements panel. And so it's my honor, if I can find my cursor, to introduce our great panelists. And so we have I'm just going to go in the order that I see them on my screen. So on my screen, I have Paul Kaler on the upper left, who's future storage architect at HPE that you just heard from. Then on my right, we have David Black, senior distinguished engineer from Dell. We have Swapna Yasarapu on the lower left, and she is leading, she's principal at Azure Storage Platform Planning. Then Ross, who is at Meta, leading, being a hardware systems engineer, leading tons of wonderful things. And Chris Sable, who is a storage architect at Google. So welcome everybody. And now I'm going to hand it over to Ross to talk us through a couple of common general comments and shared pain.
Thank you. So let's kick it off with a few things here. So a few thoughts is the device specifications as OCP, I think we view as valuable and encourage people to get involved to help increase clarity on requirements. Or other thoughts you might have. Next, let me hit on process. Further increasing collaboration increases value. And there's work going on an errata process to fix unclear stuff and have discussions around that. Mike Allison at Samsung is driving that. So if you have questions about that, feel free to reach out to him, but I know he's working hard on it. And another thought is something to think about is what are new interesting technologies that the OCP storage group should be collaborating on. If you have thoughts, I'd encourage you to bring those technologies and we can have discussions about them. Next slide here. Let's talk about some shared challenges that we all have on this panel. So maintaining SSDs and HDDs at scale is a major challenge, and the industry needs to improve in this area. This is why we're hearing all the discussion around telemetry today. It's because maintaining stuff, it's really difficult and it's getting harder. Also, I should talk about security, sustainability, and circularity. These things are all important. It's sort of a work in progress to define requirements for circularity that balance the security needs. Things like root of trust, SPDM, what features are needed for that. Things like what happens if a key cannot be cryptographically erased. These are all work in progress things that need to be thought through, and it's a very challenging problem. because clearly security cannot be compromised. Next slide.
So now we'll dive into panelist thoughts. So first up is Microsoft. So Swapna.
Thanks, Amber. Hi, everyone. I'm Swapna Yasarapu, and I'm with Microsoft, as was mentioned earlier, where I focus on driving new technologies and product capabilities for Azure storage platforms. And today, for our panel here, I'd like to bring focus to 3 areas. First is around performance scaling. So as the new cloud native applications are coming online and lighting up, and enterprise applications are migrating to the cloud, we are driving more compute and storage growth. And of course, to keep pace with it, we are driving media density scaling across both SSDs and HDDs as an industry. So one area at the same time that we do need to focus on and keep pace with is in scaling performance as we are increasing our media densities. And this is critical for the cloud. To keep our customer promises around metrics such as performance per virtual machine, performance per terabyte of capacity that we are deploying, as the density goes up, the overall performance needs to keep pace. So that's an area of focus. The second area that I like to bring some focus on is around observability and recoverability at scale. So we're practically in the zettabyte scale era as we talk about it. So huge scale. And Ross just mentioned this. I think Steve and Lee talked about telemetry earlier. So this is an area that, of course, the industry is working on, but we do need to work more on. And this is to improve our debuggability, both the speed of it and, of course, debuggability in place inside the data center. So we can drive faster debug and reduce the downtime in the data center. So anything that we all can do to collaborate around observability and recoverability is an area of focus. And the third is around sustainability. So as an industry, we do need to drive sustainability into the mainstream. So we need to collaborate around things like circularity. How are we going to reuse, recycle, think about materials so that we can actually reduce the overall waste direct to landfill, right? How do we drive power and emission reductions so that we can remove more carbon from the atmosphere than we actually emit, and we can replenish more water than we are consuming across the data centers. So those are the 3 areas of focus. Over and off, back to you, Amber.
Thanks so much, Swapna. Next up is Dell.
Hello, my name is David Black from Dell. I'm a senior distinguished engineer working on technology and standards for storage, have been for quite some time. And at this point in the session, I wind up sort of repeating and pointing to remarks others have made. So the first comment is that the common specs avoid pointless have one built for you divergence, with Paul Kaler has described at much greater length and with much greater eloquence than I can. Dell completely agrees with his remarks on why common specs are valuable for the entire industry. They enable people to spend more resources on doing productive things instead of pointless have one built for you divergence. Richer management improves drive diagnosis and debuggability at scale. We completely agree with what's going on in telemetry to improve this. We get lots of drives back from equipment in our field, and lots of those drives resolutely refuse to fail on the test bench. We have no idea why. The drive is broke, our customer's unhappy, we talk to the drive vendor, they're unhappy, and they have no idea what to fix. Richer information coming back from these drives will help reduce this set of problems and stop the problem. The source, the drive, the drives may not even come back. Upcoming features, we're not standing still on the OCP spec. 3 things that are coming. One that I've spent some time working on is sanitized verification. A couple of the specs that Eric Hibbard mentioned anticipate reading the media in an SSD after it's been sanitized. More and more SSDs can't do that after crypto erase. So there's work underway in NVMe to solve that problem. We expect to see that coming, although that will not be in the 2.5 spec. We've got to get the NVMe spec done first. Second is panic recovery workflows. You'll see some panic recovery in the 2.0 spec. The 2.5 spec will contain dotted I, cross T, exactly what to do to bring a drive back from the panic. We look forward to being able to do this and recover drives in the field, perhaps some of those drives that are getting returned and we can't figure out why they failed. And as I said earlier, we are definitely fans of the standardized telemetry. We think this helps a great deal with understanding what's going on and dealing with failures in place, as opposed to having to get the drive back and wonder what on earth is going on. So greatly appreciate the opportunity to talk about this, and back to you, Amber.
Thanks so much, David. I'd encourage the audience to start queuing up some questions that I can ask on your behalf. So please queue up some questions. Next, for panelists, thoughts continuing, HPE, Paul.
Yeah, all right. So you guys just heard from me, so I don't need to reintroduce myself. But you know, I think we're going to see a lot of overlap here between what we're all focused on and our thoughts of moving forward. Clearly, comprehensive security. You know, I could have mentioned this in the previous question as a challenge for SAS and SATA. This is one new thing that actually does need to come to SAS and SATA. So we've got a lot of focus on SPDM and the ability to authenticate and attest drives, especially NVMe drives, leveraging a lot of the PCIe CMA standards. But we really need to extend that ability to authenticate and attest drives that are SAS and SATA interfaces. So we're looking forward to, there's some work underway right now in DMTF to extend that capability and looking to be able to add that to our OCP SAS and SATA spec once that industry standard is there, and start working with vendors to make sure that they're paying attention to this and working to get ahead of implementing this so that we can have a really comprehensive security solution across all the different drive types that we have to support. And then, you know, touching on performance, we continue to see some challenges, and this is mostly for NVMe, but really want to see some better stratification of the different swim lanes that we kind of see, right? There's really kind of two different classes of NVMe drives. There's the high performance swim lane and what we call the mainstream swim lane. Some people call it Datacenter. But really, you know, today there's not a great stratification between those two swim lanes. And so you wind up getting a lot of overlap between those. And so for customers, they often ask, you know, well, why would I pick this drive over that drive? And so I think trying to get, especially as we move to trying to get more and more SATA SSDs moving over to NVMe for customers, you know, they're not going to typically move from a SATA SSD type performance all the way up to a high performance NVMe drive. That their workload typically doesn't need that. So we'd really love to see, you know, that those swim lanes get developed a little more clearly so that we can try and get customers more quickly over to NVMe, because, you know, in general, we'd love to get moving from SAS and SATA as much as possible to NVMe in the future, right? Because fewer interfaces is just better in the industry across the board. And then I think a lot of people are going to touch on sustainability. We clearly, there's a huge drive in the industry to go support this. So we definitely are very focused on, you know, how do we get the industry to focus on some like power innovations, like Swapna mentioned, I think, for how do we reduce power in the industry so that we can reduce the carbon footprint, right? And I think that's got to be focused, like even with the NAND level, you know, how do we reduce the amount of power required for writes? And with the controller level as well. So the entire SSD, you know, don't just focus on one part, but look at the entire SSD and hard drive as well to look at where we can do power innovations to save power. Because as we start moving to PCIe Gen 6 and we start trying to match the performance of the back end on an SSD, for instance, to the front end, that's going to really drive the power up. And we need to be, you know, driving power down to be able to reduce carbon footprint. So yeah, those are our thoughts.
Thanks, Paul. And Google thoughts, Chris.
Had to unmute. It's been an hour or two since I last talked. So I'm Chris Sable. I'm a storage architect at Google. Yeah, so on security, it continues to be an area of focus year over year for us. We don't take the trust your users putting us lightly, and we're continuing to invest in the area, and you'll see us continue to do that year over year. On scale, I think scale brings unique problems and challenges. We're working with our vendors to deliver awesome products. I think part of that's aligning across the industry and requirements on things like flexible data placement. We have enough challenges at scale without making everybody implement everything 11 different ways. I think that's a theme multiple people have mentioned. I think we also continue to focus on improved telemetry and debuggability, right? So it just gets back to scale and being able to successfully debug, iterate quickly at scale. So I think that ties back into the standardized telemetry that's being worked on. We see a lot of value in that. Amber.
All right, so I am going to, now we're heading into our Q&A part. So we've got 6 questions queued up from the panelists. So I'm going to quit sharing and start just asking questions back and forth. So the first question we received is on HDD roadmaps. HDD roadmaps are diverging hard. Can OCP do anything to ameliorate the HDD ecosystem chaos and help these vendors? Some of them are really struggling. We love to kick off with a hard one, right?
Paul, you want to take that? You want me to take this?
Why don't you try, Ross?
I'll take a shot at it, and then you can correct me and tell me I'm wrong. So I think there are a couple pieces in this roadmap. There are feature issues and there are technology issues. Technology issues, I don't think we are going to be able to address. That being said, feature issues, I think, are something that we can definitely address, and those are the things that we are focusing on. Paul, you want to add anything to that?
No, I don't know if that was, I couldn't quite figure out on the question where they were going with the roadmap divergence, but I think you may have touched on it, right? If it's features versus technology, I do think I agree with you. We can certainly help on the feature side to help, standardize that, again, get it into one spec and one kind of firmware, right? So I think those are things that OCP can do. I don't know how much we can drive on the technology front. I mean, certainly I think as customers, we all are trying to get more, denser devices. And so I think there's some things we can potentially do there on driving requirements around density and a roadmap, but I'm not sure if that's where they were going with that question.
And I'll just play devil's advocate of where they might have been going is we also have recently published the NVMe HDD spec and we have the SATA SAS spec. So any help that anybody sees in that arena or not?
Well, I guess I can just mention that in general, right, we definitely like being able to move in the long term to fewer interfaces, right? So like I was mentioning, if we can go from SATA SSDs and eventually start eliminating those in the industry and get everybody over to NVMe SSDs, that's great. I think hard drives, that's a longer road to get there, but I do think that that's the same ultimate goal, right? Is that we can eventually get to NVMe for everything, and then that's a lot simpler. It's one interface to test, it's one interface for customers to deal with. I think there's some challenges on the NVMe hard drive front of, certainly there to get there, but I think from a protocol perspective, getting to NVMe is certainly a good thing because that should start simplifying the entire industry, really.
Maybe I can throw in a couple of 2 cents or so, Amber. Is that all right?
Go ahead. Pop up your face, Lee.
Lee, go ahead and show yourself here.
But, so I think from our point, the question seemed to be around how the industry is kind of changing, and to date, HDDs have been pretty good about their almost like process nodes in silicon. It's like there's the next capacity, and whether that's 1 terabyte, 2 terabyte, 10, and so forth. But I think now with how technology is changing underneath, that's maybe kind of a thing of the past to some degree. And so I think as an industry and OCP specifically, maybe there's areas where we can help with variable capacity or head depopulation or things around that you kind of start to make way for the ability to do stuff with drives that are not of a, I am now 32 terabytes and that's what you get across the board. So working through that sort of ambiguity to be able, as an industry, to take up more different things like that. Might be interesting.
Thanks, Lee. Let me continue on the hard drive theme. Is there any plan to integrate HAMR support / features into the SAS SATA device spec?
Lee, do you want to? I can take first stab at this, and then
Yeah,
Ross
go for
and Lee. Okay. Yeah. So I think HAMR being a little bit almost agnostic or transparent, really, versus something like SMR, right? So SMR, I think we have a lot of requirements in there because they're very specific to how you use that drive. Obviously, the goal for HAMR would be that we don't have to care, right? It just gives us a cheaper drive at a certain density and lets us kind of continue to get higher and higher densities. So I don't think that we would call out an underlying technology like that per se in the SAS SATA spec. I think we just look at that as kind of the roadmap as it progresses and say, we want to be able to get more density, right? Performance scaling per that density. So sometimes performance per IOP. But I think the HAMR technology in general of just giving us more density, I think, is something that we wouldn't have to really specify in the spec. Lee or Ross?
Lee, anything you want to add? Or
yeah, I
turn
mean,
your camera on too, if you want.
Paul's pretty spot on there. I don't want to break the symmetry of the 6 of you right now, but
come on, this room.
So,
there we go.
Yeah, I mean, in the best of all possible worlds, HAMR is completely transparent to us as the user at the end of the day. We know how that goes, though. So as we move forward into that, as we come into use cases where we need to kind of constrain or put some guardrails on or refine how HAMR is implemented and used, then yes, we'll need to do that. But at this point, I don't foresee any of that. Crossing my finger.
Yeah, we don't want to force you to retire.
Yeah.
So in the data center SAS and SATA device specification, why is the SMR, the shingled magnetic recording zone, shall be 128 megabytes in size? Why are there not multiple options?
I guess I have to take that one, don't I? So currently, that is the Microsoft use case. We currently require 128 megabyte zone size right now, frankly, because it's HP, Meta, and Microsoft. I think I want to speak for those guys, but they have not come with conflicting requirements for SMR yet. So that's why it's there. Obviously, as we grow the pie and we have more people involved, and people are wanting different sizes, then certainly that would be a future rev of the spec that could do that.
All right. Just going back to endurance from earlier, any thoughts on endurance and reliability specifications from any of you?
Well, there's certainly endurance and retention provisions in the NVMe data center SSD spec. This continues to be a challenge for the industry because as you go to more bits per cell, the ability to do these and the trade-offs between them become harder and harder. We do see we do see this important, and there is some of this specified in the OCP NVMe data center spec already.
Yeah. Anybody else? Go ahead.
Yeah, maybe a bit of an alternate question that maybe is driven over here in terms of if there's a different way for us to specify endurance to drive more standardization. I don't know if that's a question that's brought up, right? Because they've generally talked about what workloads that endurance falls under and made a definition around it with drive writes per day. There's been thought around petabytes written overall. So we can certainly, if there's better ways to look at this, we should be open to it. But I think David kind of hit it up, right? There is, as the density goes up, perhaps there is some leeway to be given as media technologies come by. maybe we can't write 100 terabyte device as quickly as we could a 1 terabyte. So that should give us some reliefs there as well.
Yeah. I was going to say it's sort of a TCO trade-off here, right? And so it's very difficult to sort of capture that in a kind of a spec. And so there is in the long term these things evolve. So.
And
makes sense. Oh, go ahead, Lee.
Oh, sorry, and I think maybe one area is we don't necessarily always get what we expect to some degree. Each kind of NAND vendor we don't want to delve into their secret sauce, but we do want to certain things like today, I know, frankly, everybody kind of has their own reserve on program erase cycles. So they may specify to 1500, but they can actually do quite many more. And so things around that where, hey, I really want to be able to use what beyond what you're specifying here, and how we can make sure that the drive can run to the ragged end sort of thing. And we've done some of that in the spec today, but kind of standardizing that out might be an area of interest.
Certainly an active conversation, because I think also just from, for example, a cloud perspective, it's hard to say what's the workload. The workload's always changing, right? It's what customers land. So I think it's an active area where the customers are very interested in collaborating with suppliers on how do we do this better. The next question
one
was
last thought maybe around what Lee brought up and what you brought up, right? Of course, the workload is variable, but kind of putting on our sustainability hat, getting more, how do we think about, driving more, right, as an overall industry to use these devices, right? I think is another area. So anything that can be done around, what is the behavior? How do we use these? So we're not leaving anything on the table is an area that we can collaborate on.
Yeah, excellent point. Next question, security and flexible data placement, two great topics together. Is there any possibility that FTP hints could leak some information in a confidential compute environment, not endangering the encrypted data itself, but rather expose externally visible data patterns that could be tied to a specific VM and thus a user via the hints?
I guess, there's always, everything has, needs to be looked at from a security perspective. I think there's a lot of chains that would have to go, layers of compromise would have to happen. So I think maybe this summary is, I don't think we're really, it's not on our top 10 list of security concerns. Not to say we shouldn't think about it a little bit, and we have thought about it some. So I don't know if that's that. I don't know, Ross, if you have anything else.
I'll add to that. FTP does add more logging information, and so that is available. But from a security point of view, I would categorize that as low risk. But that's true of any feature, any additional information for telemetry. The more information you get from the device, that does add risk. So FTP is not unique from the health log or anything else of that nature, I would say, from categorizing in that perspective.
And I think that brings up a conversation around, is the storage device inside the trust boundary or outside the trust boundary, and what that drives around these things.
Yes.
All right, on to the next question. Changing topics. One key to circularity is in situ remanufacturing, such as the repurposing depopulation spec from long ago from Western Digital for the SATA spec. What does the panel think about the equivalent for SSD?
Lee, I think this is for you.
Well, yeah, so I think I touched on depop in one of my discussion points earlier, but yes, so depop on heads is super interesting. Again, in variable capacity situations. As far as doing that on SSDs, yes, trying the sense of today, you probably have a set of amount of spares available, and the die goes offline, and all of a sudden your spare count goes down pretty radically. There's one way of of compensating for it. The way I like to compensate for it, which is ZNS, right? And so ZNS is very flexible in the sense of you're taking all of the capacity of the drive. There's no over provisioning. If something like a die offline event happens, then I offline a bunch of zones and I know how to rebuild those on the fly elsewhere. So I think there are mechanisms today. Are there more that we could do and actually have a more of an interactive depop situation between the drive and the host for a die offline event? It's certainly an interesting area to delve into.
Yeah. Certainly worth a look because depop behaves differently in hard drives and SSDs. Unlike hard drives, SSDs are fully virtualized. So the first approximation, the depop event is a capacity reduction in the drive after you recover the data. Whereas for a hard drive that is not virtualized, you've got more stuff to deal with and some more specific things you have to do because a non-virtualized virtualized component has failed. So I think it's interesting for SSDs, particularly if we start to see end-of-life variability in die lifetime. Then depop and capacity reductions starts to be an opportunity to get some more life out of what's left of the drive.
Thank you very much. Next question for Paul. Besides HPE wanting to charge differently, why does NVMe need two different performance stratifications? If the highest performance meets all segments, why bother trying to downshift? The user can do so depending on their power requirements.
Yeah, so it's actually more expensive, right? I mean, if you have to design a 16-channel NVMe controller to support the high performance to saturate a PCIe Gen 4 or Gen 5 front end, that actually costs real more money. You have to support multiple channels on the back end of that SSD. So if your workload doesn't require that much performance, you're just basically spending a bunch of extra money if you're the customer to be forced into, and what's that really is going to wind up doing is that'll mean that we have SATA SSDs forever. Because if we maybe had started with that to begin with, we could have maybe done one NVMe SSD and maybe we could have forced people down that road. But with SATA SSDs being there, those are super cheap, right? They're all like 8-channel controllers. They're very inexpensive devices. If you now go and say, we're going to support a super high-end NVMe, and that's going to be the only option customers have to go to, they won't move, right? We're going to keep having to support SATA SSDs forever. So ultimately, that's the reason, right? It's an actual real cost, and it's basically you can't make it that efficient either. So you wind up with a carbon tax. Basically, you're going to have additional power that you're going to be burning that you don't really need for your workload. So it's just kind of right sizing your needs for performance is ultimately what it comes down to.
Another related thing to that is that with the humongous SSD sizes we're seeing on vendor roadmaps, got people talking about drives well north of 100 terabytes. We're going to see some form of stratification between those who are interested in I/O performance for relatively hot data and those who are interested in capacity for relatively long-lived data. And there's a really good opportunity industry here that people will start biasing the drive designs towards one or the other of those use cases.
Thank you. Would it be possible for each revision of the OCP spec, the official as well as the beta, to be available similar to the way NVMe archives these spec versions for NVMe on their website? It's hard to find the various previous versions of older OCP specs. Also, a summary of differences would be extremely helpful for vendors. For example, what changes need to be considered in the newest OCP specs? Perhaps consider this as a standard or new requirement ID for those making changes to the spec, smiley face.
So I heard a bunch of things in that question. So let's walk through some of these. So for finding the old revisions, if you go on the OCP contribution portal and you click storage, There are not a lot of listings there. You should be able to find the old versions without too much difficulty. Now, the next thing I heard is a bulleted sort of feature list of what's new. I think that's something all us authors we can talk about and discuss. There's probably more of the questions I've forgotten, but maybe somebody else wants to hit on the rest of the question.
Yeah, I think the one I heard was beta versions, and that goes back to some of the discussion about how we change up OCP IP requirements and being able to do feedback and errata more openly in the storage group, but we can't do that yet. So.
Yes, Mike Allison is working on that, and you know, all I can say is he's working hard on it.
Yeah, I think the one thing I might add, the beta versions, the way I interpreted that as well was kind of the versions that aren't contributed. And those are really kind of meant to be working drafts. So I don't think we would want to have those necessarily. There's maybe some conflicting requirements there, but when we finally get it finished and we contribute it. So I think it clearly, all the previous contributed, we want to have that out there. But the working drafts, I'm not sure that that's a great idea, because that could cause some industry confusion about, something's floating out there and maybe they didn't check to see if there was an actual contributed latest version. But maybe I misinterpreted the beta comment, but yeah, I don't think we want to have every single little draft revision out there.
Yep.
Thank you.
Sometimes people don't want to see the sausage being made.
That's right. Yeah.
All right, next question is there any value to putting SSDs on a CXL interface, perhaps for computational storage, or is NVMe and PCI Gen 6 optimal for most or all use cases?
I could start on this one and other people can jump in. So I think from kind of the one interface to rule them all, right? We kind of talked about if we can move everything to NVMe, that's great. I think that, if in the future somehow we thought CXL was going to be the new interface, that would be good for everything. I think there's maybe some uniformity benefits for doing that, but I don't think that I've seen real world actual performance benefit or something along those lines. PCIe, is good from a performance perspective for NVMe. I haven't seen major improvements. Now, I think when we start talking about different use models of not just block SSD, but adding in computational storage, like the question mentions, I think then there might be some capabilities where you might have some benefits to having a CXL interface to do specific accelerated cache coherent type operations. But as a standard NVMe block device, I don't see a big advantage to going to CXL.
I mean, a good way to think about this is step back and ask, what were the problems that these technologies were invented to solve? What are they really, really good at? And it's sort of in their names. The P in PCIe stands for peripheral. It's a great interface for connecting peripherals, say SSDs. I mean, as Paul sort of says, it's not broken, does not need to be fixed. So why does CXL exist? Well, the C in CXL stands for compute, and you can also think of it standing for cache and coherency. It delivers its biggest benefits when you're dealing with memory, and you're dealing with memory in a fashion where you want it to be cache coherent with the processor. So to the extent that there is an SSD device that has a lot of onboard directly addressable memory, you've heard somebody's talked about it as memory mode SSDs, then CXL starts to do things that PCIe is ill-suited for, and that's where you'll start to see CXL SSDs emerge, where they deliver some technology and some benefit that you can't get to with PCIe.
All right, the next question is somewhat similar, so I don't know if we need to cover it. It was any roadmap considerations with CXL technology, which I think you guys just covered, so maybe we skip over that one. And then we have two similar questions, so I'll just ask the first of that since the other is pretty similar, just like in our CXL topic. What are the plans moving forward for the OCP NVMe boot spec? Ross, do you want to start and I can then add?
Sure. For the boot spec, I think we're still working on industry convergence on that topic. For Meta, I think we're moving in the direction of using the data center SSD drive for boot, as we feel there's good industry synergies in that direction. But that does not mean other people feel the same way, but other people are welcome to express other opinions. Amber, you want to comment?
Yeah, from a Google perspective, Google and Meta together developed the Hyperscale NVMe boot spec focused on M.2. I think we've already been trying to drive good synergy between the data center SSD spec and the Hyperscale spec. For example, on the security requirements, we've already been trying to harmonize those. I think especially suppliers in the industry are aware that they're getting slightly different requirements on M.2 from lots of us. Whether they need capacitors or 22 by 80 or 22 by 110, or single-sided or dual-sided, and small capacity, larger capacity, lots of fun there. So I think what we're having to do is Google continues to be focused on and committed to the Hyperscale NVMe boot spec. However, I think we're also trying to work with suppliers of the very real problem that they're getting, that each of us has varying requirements, that is requiring different capacities and different sizes and whatnot. That's really challenging for suppliers. So I think we have work to do there as an industry to come together over the next 6 to 12 months of how do we continue over the long term. Okay, next question.
Let me add one other comment just on the boot thing. I should also add, to be fair, the boot spec is really a subset of the data center NVMe spec. So we shouldn't think of them as competing polar opposites. Rather, we should think of one as a simplification of the other, in my mind. So I should add that.
And I think that the Dell view of this is strongly endorse where Ross is going of converging the specs. We do use M.2s. They're not just boot. They're boot and they're vault, and they solve certain nasty form factor problems at the edge. And we just assume procure them against NVMe data center spec, please.
And I think the dissonance that everybody's hearing is some that don't need as much reliability, as much capacity, would prefer to, in theory, have a lower cost, just to, the kind of discussion we had about NVMe stratification. And so we're having fun of how do we come together.
Yep.
All right. The last question I have received, so if anybody wants to submit 1 or 2 more questions, we can probably take 1 or 2 more. But the last I've got so far is, in the past with SATA device-initiated power management, a blast from the past, DIPM, we were able to really reduce drive power with aggressive use of drive autonomous power state transitions. There is an exit latency trade-off, of course. What is the vision of this panel on the matter of drive power modes and their utility in reducing data center operational power?
I can kick that off. So I know for our customers, having the drive magically go into different power states and have different performance is a really bad thing. Our customers like to have very consistent performance. So we really more prefer on the host side of power management. So if the host, that's I think certainly something we see with the NVMe power states and the DSSD power states that we kind of created for the NVMe data center spec. We really want to be able to support that so the host can configure that, and then of course hopefully get benefits there in power savings. But we really don't like it, or I should say our customers really don't like it when the drive just kind of randomly goes into its own power saving modes, because it almost always is at the wrong time. It's very hard for that to work without the host intervention.
Let me add to Paul's comments. So if we look at this historically, DIPM, DevSleep, these features were targeted for laptops running on battery. And the goal was for client devices to have longer battery life. And so steady performance was not such a big criteria, as it was more of how long can my battery last in my laptop. When you go to the data center, performance is everything. And you really need to manage your performance for stable performance. And because we all, you know, when we're looking at some application and we're waiting for it to load, nobody wants to wait. They want it now. And so consequently, that leads to a power model that's much more power budgeted, or I want you to live within this power budget and you set the power state, which is a very different power model than you'd use for something running on batteries. So that's what drives a data center wanting to just set the power state and have it set at a particular level. It's not wanting to have that latency impact and negatively impact user experience.
Yeah. Maybe we can actually get people to implement transitional energy now. But I have to digress. So yeah, I think DIPM is this people have said is very problematic in the data center because of, you know, the changing workloads. But that being said, HIPM, I believe, will be more and more important going forward, so that the host can, number one, stay within that power budget, like Ross was saying, but also too, when it knows that the node is idle, that it can go to a very low power state on devices. So, you know, there are always certain, you know, amount of stuff. Obviously, we want to run everything at 100% all the time. That doesn't happen in reality. And so there are, I believe, some good areas where we can save some electrons when we can.
So I want to thank Paul, David, Swapna, Ross, Chris, and Lee. I would truly love to comment on the collegiality and collaboration to try to really come together. We are really trying to make everyone's lives easier and provide that clarity and try to get to simplified as much as we can. So really appreciate everything that folks have been doing. So now I'm going to shift over to the closing. So let me show the couple closing slides. And so Ross and I would just really like to thank everybody for joining us today. And so a huge thank you to our sponsors, Fidoo, Silicon Motion, and Micron. So thank you guys for supporting us and this effort. And really big shout out to our OCP support team, Callie, Kate, Kevin, Michael. We couldn't put on this anything at OCP without you, and so we really appreciate all the support. Thank you to our great speakers. We really appreciate all the dedication and time that went into preparing for today. And so as we go forward, we just wanted to do a quick call out of we look forward to the carrying forward great ideas today, such as the telemetry, how does regulation impact us, all those other pieces and the great questions that each of you provided. And if you haven't noticed, the abstracts the call for abstracts is already out for the OCP Global Summit that will be in San Jose on October 17th through 19th. Please get your abstracts in. They're due by June 16th. And we're excited to have another great conversation in October. So thank you so much.